talking about how do we determine hybridization, right? This is the fun, easy part. Trust me, it's easy, okay? Now, here's how you do it, okay? What's an easy way to determine hybridization? Look at how many electron groups an atom has. Now, let me just say, I don't know if this is taught like this in most classes, but this is how I do it. So, what is an electron group? Okay, well, first of all, I'm making up this word, so I don't even know if it's a real word, but this is how I'm going to describe it. So an electron group can be a single bond, and I'll go more in depth in a second. If this doesn't make sense, don't worry. Just stick with me, it'll make sense. Okay, so a single bond counts. Single bond counts as an electron group. A double bond counts as an electron group. A triple bond counts as an electron group. And a lone pair of electrons counts as an electron group. What does not count as an electron group? That's a great question. The answer is positive charges. And that one kind of makes sense because remember, a positive charge is created because of the absence of electrons. So it would make sense that you wouldn't have the absence of electrons count as an electron group. And then also a radical electron is not an electron group. Why is that? You know, that's a good question. I don't really know. The answer I'm going to say is because it's not an electron group. It's just a single electron, right? A radical has one electron in it. You have to have at least two or more to be an electron group. So a single bond, well, a bond is made up of two electrons. A double bond has 4 electrons, right? A triple bond has 6 electrons, right? And then of course a lone pair also has 2. So you need at least 2 electrons to be considered an electron group. But, you know, let's see what we got here. Okay, we're going to jump into some bond geometries real quick and just talk a little bit about them, and then we're going to actually practice what we learned up here, right, where we learned how to determine hybridization, right? But we're going to really quick take a little side note about bond geometries, and then we'll jump into practicing determining the hybridization of different atoms. Okay, so let's pause that and talk about bond geometries, which is still related to hybridization. In fact, geometries are caused by hybridization. So whether a carbon atom is neutral or charged, its molecular shape can be determined. Its molecular shape can be determined by its hybridization. That's what's so cool about hybridization. If I'm really familiar with hybridization, I can figure out the hybridization of a carbon, and then boom, I know the molecular shape of those directly surrounding atoms that's attached to that carbon. By finding an element's hybridization, you can determine the favored bonding angles. Okay, let's start with carbon. So if you have a carbon and it's sp3 hybridized, you know what, maybe we should do, because you still might not know how to identify sp3 hybridized. So what we're going to do is we're going to actually come back to this section. Okay, we're going to do a few examples first, okay, of how to determine hybridization. Okay, so let's start with this carbon right here. So the first thing you do is you count how many electron groups that carbon has. So let's zoom in here. We've zoomed in. So this carbon has a single bond, and on the other side it has a triple bond. And remember, a single bond counts as an electron group, and a triple bond also counts as an electron group. So both of these are electron groups. Therefore, how many electron groups does our carbon have? Well, the answer is that it has 2 electron groups. Okay? And that means that it's going to have a hybridization that accounts for those 2 groups. Okay? So, remember what I said earlier about hybridization, where the number of orbitals you put in to hybridization equals the number of orbitals, of hybrid orbitals, you get out of hybridization? It's the number of hybrid orbitals we want to match the number of electron groups. So for example, if I have 2 electron groups, that means that I want 2 hybrid orbitals. 1 hybrid orbital will be used for this side, and 1 hybrid orbital will be used for this side. Okay, and we're not going to jump too in deep to that because there is more information about that. We're just doing how do we determine hybridization the quick and easy way, okay? So, if this carbon has 2 electron groups, then it needs 2 orbitals to hold those electron groups. Okay? And so what hybrid orbital do we have exactly 2 hybrid orbitals of? Well, the answer is sp. sp. Because remember, how do we make sp orbitals? By hybridizing an s orbital and a p orbital. And remember, the number of orbitals you put into hybridization is going to be the same number of orbitals you get out. So if I put in 2, I get out 2. Since I have 2 electron groups here, that's what I want. Now, as a side note, these hybrid orbitals are what's used for making the sigma bonds, okay? And so the sigma bond here is using that one of the sp hybrid orbitals, and the sigma bond on this side is using the other sp orbital. Oops, sorry, not sp2, sp orbital, okay? Then how do we make these pi bonds, these 2 pi bonds here and here? Well, remember, pi bonds are made using p orbitals, okay? So, that's just a side note. All right, so what's the hybridization of this carbon? The answer is this carbon is sp hybridized. Okay, practice will help. Okay, so let's do another example here. Let's look at this oxygen. So first of all, we have not drawn everything that is on this oxygen, right? The oxygen has 2 lone pairs that nobody drew. But remember, sometimes people don't draw lone pairs. You're expected to know when there needs to be lone pairs and when there doesn't. So, how many electron groups does our oxygen have? Well, 1, 2, 3. The answer is 3. So if it has 3 electron groups, how many hybrid orbitals did it need? Well, the answer was 3. And so what hybrid orbital can give us 3? 3 hybrid orbitals. Well, remember, if we use sp3, that means we put in 4 orbitals. We don't want 4 orbitals, so it's not sp3. If we have sp2 hybrid orbitals, that means we have an s and 2 p's. And that is 3. So that's exactly what we want. If we hybridize an s orbital and 2 p orbitals, we will get 3 sp2 orbitals out of it. And since this oxygen has 3 electron groups, it's going to have a hybridization of sp2 hybridized. All right, so sp2. Okay. Let's add another arrow. Let's add this arrow right here for this carbon. Okay, so how many bonding groups does that carbon have? Well, it's got a single bond here, so that's a bonding group. Single bond here, so that's a bonding group. And a single bond here, so that's another bonding group. But What you need to remember is when you have an invisible hydrogen, okay, or when you have multiple invisible hydrogens. In this case, we have one invisible hydrogen, okay, so actually, there's the fourth bonding group. So there are four electron groups. Electron groups. So if we have 4 electron groups, then how many orbitals did we need? Well, we needed 4. So we are going to have to be sp3 hybridized. Okay, right? Because sp3 has 4 orbitals hybridizing together, which then produces 4 sp3 hybrid orbitals. And we needed 4 of them because we have 4 electron groups. Okay? All right, let's do another one here. Let's do this carbon. Let's do it, this carbocation, let's do it in yellow. Okay, so how many electron groups does that carbocation have? Well, it's got a single bond, so that's 1, another single bond, so that's 2. But we know because it's a carbocation, it has to have 3 bonds. So there is an invisible hydrogen here, which means there's the 3rd electron group in that 3rd single bond. So if we have 3 electron groups, then what will be the hybridization of that carbon? Well, if we've got 3 electron groups, then we need 3 of our hybridized orbitals. So that means we will be sp2 hybridized. Okay. And let's do this nitrogen. So let's look at this nitrogen over here. Now what stinks about this nitrogen is both of the hydrogens that are bound to that nitrogen, we didn't draw the bond. We just put H2, which, you know, a lot of people do because it's easier to write. But when you are figuring out hybridization, especially when you first start doing this, it's easier to visualize your electron groups if you actually draw out all the bonds and all the lone pairs. So what I'm going to do, so first of all, that nitrogen has 3 bonds, which means it has a lone pair that nobody drew. So let's draw it in. All right, but instead of drawing those hydrogens right next to it, let's erase those hydrogens and let's draw the bonds to them. So instead of drawing it like this, I would, in my head, imagine it like this. Like that. So, how many electron groups does this nitrogen have? 1, 2, 3, 4. The answer is 4. So with 4 electron groups, means we need 4 hybrid orbitals to accommodate each group. And if we need 4 hybrid orbitals, then that means sp-pp, we need this nitrogen to be sp3 hybridized. There we go.